You guys look scared. It's a raven. Nevermore. Yeah. Okay. You guys have been used to expressing functions as f of x. That is now going to change in this chapter. This is going to be new, and it's going to take a little bit of adjustment. But the first type of change in this is probably the simplest, and it's one that whenever I make worksheets with graphs that are not functions, we have to do this with the program that we use. Because the program we use is the first hit that comes across when you search for graph on the internet. It usually is on Google. And this person that developed it enabled it as a plugin into Word, so I can actually like go back in a document and edit a graph instead of just insert a picture. So it's really, really, really nice for us. But it means that we have to put things in parametric equations if we want to show certain things. So this problem specifically says, in a pumpkin tossing contest, a contestant won the catapult by using 2 telephone poles, huge rubber bands, and a power winch. But that's neat and not really relevant. Suppose the pumpkin was launched with an initial speed of 125 feet per second at an angle of 45 degrees from an initial height of 25 feet. And the question asks you to write a set of parametric equations for the motion. So a parametric equation is essentially when, and I'm going to kind of try to pick apart here, when you have a graph of anything and I have an ordered pair on that graph, that ordered pair is not necessarily x comma f of x. That would be the old way of showing it from a function perspective. A parametric equation means that you have a function in terms of an independent variable and another function in terms of an independent variable that's outputting the position. You have 2 separate functions, and you're plugging in the same variable into both functions. One of them outputs x, one of them outputs y. Every single graph that you do can be done in terms of a parametric equation. Even as something as simple as a line or a constant function can be done like that. Now, that said, sorry, I'm going back to one case of where I just want to see where I did this last year. Give me 2 seconds. I was trying to get this up while talking, and done. That said, this type of function right here is a function that inputs a real number. This is a little college notation, and it outputs a 2-dimensional real number, an xy. In other words, it's inputting a t and it's outputting an xy. You have functions that have done that before, functions that input a number and output 2 numbers. I years and years and years ago did something with you guys. It was a worksheet you guys had in Algebra 2, so sorry, Sean. But I would do 7 and then output 1 and 6, and then 8 and output 1 and 7, and 11 and output 1 and 10. And it's one of those like fill in the patterns. This is a very simplistic one. But the function that inputs a single variable and outputs 2 other variables or 2 other numbers is something you guys can kind of perceive of. This inputs t and outputs xy. Which is what makes it just a little bit different. Now, to get this function completely correct per se, what I want to say, I want to kind of do a few things with this. It says write a set of parametric equations for the motion. And it says it's launched with an initial speed of 125 feet per second. Now, that initial speed of 125 feet per second is at an angle. So this angle of 45 degrees, its initial speed is launching up at 125 feet per second. What you guys should know about vertical and horizontal components of this is that I want to break that down into both of those. So its initial speed in terms of x, we'll call it v sub x 0, like its initial velocity in terms of x. How would I find that given this? Good, 125 cosine of 45 degrees. The velocity function in terms of x would then be that initial velocity. 125 cosine x would just be 125 over root 2. And if it's horizontal, that's actually the constant velocity horizontally completely. So sorry, not v of x. We're going to go v of t, v sub x of t. That would be multiplied times t. So this is the velocity. Ooh, I'm actually messing this up completely. That's the position in terms of t. Now I'm better. Sorry, Hudson. Multiplying velocity times the time. Y is a little bit more complicated. Many of you guys know, and I'm just going to throw this down for those who don't. You don't have to memorize this, that the projectile motion equation, when influenced by gravity, is something like this: 1/2 at squared plus v sub 0 t plus s sub 0. And in this case, it'd be plus y sub 0, because I'm actually talking about a y position. I'm in feet. Sorry. What's the constant of gravity due to in feet? You guys know negative 9.81, but do you know what it is in feet? Acceleration due to gravity is negative 9.81 meters per second squared, which is also the same as negative 32.2 feet per second squared. Because feet and meters are used a lot in math, you guys should probably know both at some point, but not yet. So I'm going to plug in negative 32.1 t squared plus, I need an initial velocity for the y. So let's kind of go back and talk about what vy of 0 is. If vx sub 0 is 125 cosine of 45, vy 0 is sine 45, which is the same thing because the sine of 45 and the cosine of 45 degrees are the same. So that's also 125 over root 2 t plus the initial height, y sub 0, which, yes, it gives you that right here, and that is 25. So to sum this up, and I'm going to kind of simplify this over here, x of t could be 125 over root 2 times t, and y of t is negative 16 point, sorry, this would be 32.2, so negative 16.1 t squared plus 125 over root 2 t plus 25. This is an example. This is a little bit more complicated of an example than you guys will have to do, but this is an example of how the motion can be broken down into horizontal and vertical components. Inputting a particular time and outputting a position of this object wherever it is. Yes, this is artificial. It presumes no air resistance. It presumes that it's going to go at the same velocity horizontally until it's stopped, and the vertical is completely not influenced by that. But in general, this is kind of what you guys can expect. Use the equations to define how far the pumpkin traveled. That's a different question. So how far the pumpkin traveled is its horizontal distance. But I would want to know what? How could I use this to figure that out? I'd first want to find the time when what's true? When y of t is equal to 0. So I would set y of t equal to 0. Then once I would get that, what would I want to take that and find? I'd find t when y is 0. Then what would I do with that t value? Yeah, plug it into x of t and get something. So I can find the x spot when y was equal to 0. We're not going to do that at the moment. We have a 40-minute class, and I want to move on to kind of some actual stuff. This would be a calculator problem because of the radical. If you were doing this and solving this with a quadratic formula, what I would recommend doing would be, at the very least, multiplying both sides by root 2 once you set it equal to 0. So you can have radicals not in the denominator while you do that. But okay, the next part is something you guys will have to do. We're going to practice working with parametric equations first, and there are going to be a few components to this. The first is, what does the curve actually look like? So here's a graph, x is equal to 2t and y is equal to 4t squared. I'm going to replace that lingo with x of t is equal to 2t and y of t is equal to 4t squared plus 2. A parametric equation is not in parametric form unless it's set equal to x and y. You no longer have y as having to be the thing that's set equal. It's two equations, one set equal to x, one set equal to y, both in terms of the same independent variable. Got it? The single best way you guys are going to have to get a graph of what this might look like would be a t-chart. I have no idea why there's a second dash there. That's bothering me, and I have to delete that later. But since it's going from -2 to 2, really it's not too difficult to plot -2, -1, 0, 1, and 2. And I'm going to put this as t. And you can do two things for the second part of this t-chart. You can put an xy ordered pair like this, or if you prefer, you can do x and then y as separate little pieces there. I'm going to change it up this year and do x comma y because I kind of like that better because that's actually what you're inputting. You're inputting a t and outputting an ordered pair. So -2, go ahead and start plugging these things in. I'll try to somewhat keep up. So -4 for x, and then -2 squared is 4, 16, plus 2 is 18. So you got -4 comma 18. -1 is -2 and 6. 0 and 2. 2 comma 6 and 4 comma 18 because of the symmetry. What's interesting to me on this, and yay, even odd, is that you'll note that the x function is an odd function and the y function is an even function. This gives you the same y values for opposite x values, and the breakdown of this kind of actually shows how that's working. What shape is this? Yeah, it's just a parabola. It's a basic parabola. If I scale the y's by 2, I'm going to put a little times 2 there, but I keep the x's the same, then I just get, oh hell, let's just scale everything by 2. Then I have a nice gridded out one. So -4, 18 becomes -2, positive 9. It puts me here, then here, and then symmetry, and here. And I will graph each eta because I really am not good. Oh, sorry, I need to put 0, 2. That's why it wasn't working well. Now it looks better. Do not put make it go through and put arrows on the end. That is a restricted domain. But there is one more thing that I need to include. What do you think that might be? Close. Let me just explain something here. There is actually a difference between this and if I were to say x of t is -2t and y of t is 4t squared plus 2. They would actually generate exactly the same ordered pairs, but there is a slight difference between them. If I were to graph this second one, t, x, y, plugging in -2 would give me the ordered pair 418. -1 would give me the ordered pair 2, 6. 0 would still give me 0, 2. 1 would give me -2, 6. And 2 would give me -4, 18. What is the difference between the two of these, even though they've generated the same ordered pairs? I mean, one person, guys, because with the headphones on, I can't really. Yeah, Quinn? The time at which the points occur. So how could I indicate that on this first graph? What's a way that I can show not just how it drew, but the order? Put a net what? Close. There's a simpler one. I'm just curious if any of you guys have seen this. What I'm going to do is I'm going to put these down. I'm going to put arrows. You don't have to crowd it with too many of them, but the arrows indicate the direction in which this was drawn. I'm going to replace these arrows with orange ones so they correlate to the orange graph orange one, like writing I had. If I was doing the green ones, they would be in the opposite direction. Does that make sense to you? We go from smallest time to biggest time. T is my left to right here. So when it says t from -2 to 2, we start from -2 and then we go up to 2. You don't ever do it the other way. And if you want to switch the direction, I could switch the x's around and make them different signs, and then it draws the graph in the other direction. So a parametric equation, the weird thing about it is it's not just the shape it is, it's how it's drawn. Does anyone have a TI-84? The old school TI-84. This actually has one advantage over the Inspire. And the advantage of the 84 is its slow processor. The slow processor, when you graph a parametric equation, actually shows it graphing. And it shows the path that the object takes. The Inspire's processor is too quick, and it just puts it all in at once. You can't see it happening. So there are ways that we've tried to kind of deliberately slow some of these things down. So you can see that if it drew a spiral, it would actually do this. Like the 84 is really neat when you see it draw something in parametric mode, whereas like the Inspire would just appear. And that's not as cool. It's why Mr. Keelan says the calculator sucks. That's not true. Okay. Next thing, eliminating the parameter. So T-charting is all fun, sort of, but it's not. And a way to eliminate the parameter, what it means is combining the equations into a classic one and then determining the direction afterwards. So to combine these, think about it as like almost like a system of equations. One way to do it, not the only way, but one way to do it is to set both equal to t, and then just bring them together. You're going to do this with whatever means you have available. So for this, I know that like in this first one, it give me root t minus 1 is equal to 1 over x, or x is equal to, well, let's square both sides now. T minus 1 is equal to 1 over x squared, and t is equal to 1 over x squared plus 1. And in the second one, I don't really need to do that. I want to make it a function in terms of y, so let's not set them both equal to t. Let's just plug this in. Y is equal to 1 over x squared plus 1 over, plus 1, sorry, over 1 over x squared plus 1 minus 1. Let's multiply both numerator and denominator by an x squared, so that I would get y, let's see, that'd be a 2x squared plus 1 over 1, or 2x squared plus 1. Which you know how to graph. That's a vertical shift and a stretch of a basic like parabola. If you kind of remember your base points for a parabola, shift up 1. The next point was like over 1 up 1, but a stretch of 2 would be over 1 up 2. And the final one would be over 2 and up 8. It puts you right here. Let's check that. Plug in 2 and I get 9. Yep. So my graph would kind of look like this. Actually, it'd look completely like this, but we need to be careful about how our graph looks. I'm going to sketch this, but remember, I can erase my pen marks pretty cleanly. So looking back at the parameters, x is equal to 1 over root t minus 1, and y is equal to t plus 1 over t minus 1. Let's talk about domain here. Give me any domain restrictions you know from the two of those. Go. T has to be greater than 1. T cannot be 1, can it? So if t is greater than 1, let's just start graphing from 1 and see what's happening. As I plug 1 in, I would get, well, I can't plug 1 in, so let's just try 2. Just get an idea of what this looks like and where I'm starting. 2 would give me the ordered pair 1, 2, 3, which is this ordered pair. Which ordered pair am I approaching as x is 1? Well, we can check this based on this right here. Somewhat. When t is 1, or t is greater than 1, let's think about like 1.1. Let's do like a t is equal to 1.1. So this is when I'm really, really close, and this is t right here. 1.1 gives me 1 over the square root of 10. It's really, really a tiny number. So it's basically like, I'm basically getting close to 1. I'm getting almost an x is equal to 1. I'm trying to kind of do this without talking about limits. I'm trying to think of a good way to get to this when I'm not talking about limits, but I don't think I can. Or kind of reason through why you're getting close to this. This is your kind of asymptotic point that you're getting to, though. Like you're getting infinitely close to 0, 1. I wouldn't completely expect you guys to know that because I don't want to talk about limits just yet. So I'm not going to cry if you start at 1, 3. But you do have that entire space where t is close to 1. Or you can get that. I suppose you can kind of plug 1 in here. Yeah. But well, t can never be... Or not t is 1, sorry. X is 1, y is... Or x is 0, y is 1. Yes, Paige?
Why did you erase the left side?
Well, I know that like I'm never going to output any negatives. So like think about what's happening with x right here. I mean, I guess one way to kind of look at it is to talk about this in terms of range. So whatever I plug in here, x is going to have to be positive. It's going to be impossible for x to be negative. The smallest that x can ever be is 0. This will be kind of like, let me kind of do it here. This will be a way to talk about it without limits. If I look at this particular equation right there, I know that whatever t value I get, x also must be greater than or equal to 0. And actually it has to be greater than 0 because it's going to be impossible for 1 over anything to be equal to 0. So since x has to be greater than 0, that can be a reason why this has to be an asymptote. Don't overthink it. Your problems are not going to be that difficult in terms of determining where it's approaching and where it's not. But it's good mathematics to kind of start to raise and like look at your different reasons about why your graph can't be a certain point and why it can't be left at this. It can't be over here because x can't be negative. Not in the original equations. Finally, since I'm moving in this direction, you can start to plug in successive t values and see that you're actually growing in the right direction. So we're going to put an arrow to indicate that. Yes, Paige?
So wait, can't x not equal 0.5? So why would there be like a line?
Oh no, x could be 0.5.
But like, wouldn't that be negative? Like you can't take x or the square root of a negative.
Well, what? X can be negative. T can't be 0.5. But x could be 0.5. If I had x be 1/2 equals 1 over root t minus 1, that would occur when t is equal to 5. It's confusing because your graph doesn't graph t. And that's what you kind of have to keep straight. That at no point on the graph do you actually see t. You see the result of when you plug t in. Yes, Ethan?
As t gets bigger when x approaches 0, so why are the arrows going up instead of closer to 0 as t gets bigger?
As t gets bigger.
You get closer to 0, 1. Your x value does that.
You're right.
Yeah.
And I'm going to redo this, how I say this next year. This does go the other direction. Aw. You do get asymptotically closer to 0. Because as t gets bigger, in this particular graph, x approaches, what I'm going to say is, we'll use a little bit of limit terms here. As t approaches infinity, x approaches 0. And as t approaches infinity, y approaches. T plus 1 over t minus 1 is 1. So, yeah. Nice catch, Maluccio.
So the arrows not only, so the arrows say as t increases, what happens to your x or y?
They do. They indicate as t gets bigger, what are you approaching? I might do a different example next year. Okay, eliminating an angle. This one's more fun. I like these because this is the true conversion of polar coordinates. This is kind of the start, the very beginnings of polar coordinate systems. when you graph this and look at this, if x is equal to 5 cosine of the angle and y is equal to 3 cosine of the angle, this means as you plug in an angle, the most that x can be is 5 and the most that y can be is 3. Can you visualize what shape this might be? I'm plugging in a particular angle and outputting an x. Think about when that angle is 0, x is maximized and y is minimized. X is 5 and y is 0. When I plug in an angle of pi over 2, y is maximized to 3 and x is 0. When I plug in an angle of negative pi, I get an x of negative 5, right here, and a y of 0. And when I plug in an angle of 3 pi over 2, I get x is 0 and y is negative 3. What shape is this? You get an ellipse. We're going to get back to the graphing of that here in a second, but let me show you how to combine these. I need an identity that talks about x and y. I need something, a trigonometric identity, that basically makes it so that x and y can be combined into a single thing. The identity we're going to use is x squared plus y squared is equal to r squared. But that's not useful because there is no r here. So let's go back to a variant of that one. Cosine squared theta plus sine squared theta is equal to 1. So let's take each of these and solve them for cosine and sine. Cosine of theta is equal to x over 5. Sine of theta is equal to y over 3. And plugging each of those in gives me x squared over 25 plus y squared over 9 is equal to 1. And boom, you have your ellipse. Same idea, but an interrelationship between the two. And as that ellipse goes from an angle of 0 to 2 pi, the tracing of the ellipse happens in this direction. One complete cycle all the way back. The thing to remember when doing those problems is going to be this thing. So if you're stuck on one with sines and cosines, go back to your identity of cosine squared plus sine squared equals 1. Yes, Pahina?
Can you repeat like why the arrows are going that way?
They are because of the domain restriction here. Even though I'm not truly graphing the angle, you can kind of see that when x is 0, or when theta is 0, sorry, when you have a theta equals 0, you're here, and we start sweeping in this direction, moving all around. Now, one of the most maddening questions for me is asking you guys to split them up into parametric equations, because when you do that, and when you split them up, you can do this in an infinite number of ways. I'm going to ask you guys to keep it as simple as you can. So if I gave you a question like this, the stupidest and simplest way is that you let x of t equal t. That's what the first one's saying. I'm going to let you guys do that once on one of yours. If I ask you for multiple versions, I'll let you do that once. If x of t is t and y of t would then be t squared plus 2, yes, that is a parametric equation. It's a stupid one, but it counts. I might ask you guys how you reverse direction on that. What's a way to change direction? Yeah, x of t is equal to negative t. And then you have to make sure that y of t is negative t squared, which is the same thing as t squared plus 2. So one of those gives you a forward direction parabola. The other one gives you a reverse direction parabola. Now, it's possible that it could actually give you what the parameter is. It says t is equal to 2 minus x. In which case, that actually defines x of t is equal to what? 2 minus t. Be careful when giving me your parametric equations that you don't give me t equals. You need to give me x and y equals. I won't cry if you don't put the x of t or y of t, but I prefer it. I know that y of t is then equal to 2 minus, let's see, y was x squared plus 2. We're still in that same problem. X is equal to 2 minus t, so this is 2 minus t squared plus 2. It doesn't really matter. What I would probably prefer for this would be one of two things. Either you change it to t minus 2 squared plus 2, which you guys should know that 2 minus t squared and t minus 2 squared are the same. So it's better to be in the form of t minus 2, just for a number of reasons. Or to go ahead and multiply it out. T squared minus 4t plus 6. I'm going to do a little C here and add this to the notes next year because I want to do one more where what I would call this would be, let's make this more of a composition of functions. So if I'm creating a third one and I want this to be representative of a composition of functions, that means that I'm going to let t equal x squared. That's my condition. And then if t is x squared, what's y equal to? T plus 2. And then all you have to do is just simplify the x equals. So you get x is equal to root t, y is equal to t plus 2, and then you've got another version of this. Okay, last example. Converting them into parametric equations. The hint here is to use a Pythagorean identity. What identity do you think that is? X squared what? Yeah, x squared plus y squared equals r squared, which in this case is also sine squared plus cosine squared is equal to 1. So let's make this equal to 1. X squared over 16 plus y squared over 16 is equal to 1. X over 4 quantity squared plus y over 4 quantity squared is equal to 1. And now I simply need to pull this out and say x over 4 is equal to sine of theta, and y over 4 is equal to cosine of theta. So my parametric equations will be x of theta is equal to, oh, that should be reversed, my bad, cosine sine. X of theta is equal to 4 cosine theta, and y of theta is equal to 4 sine theta. I'll give you something that you guys hopefully are kind of figuring out. In an ellipse, which a circle is a kind of, x of theta is equal to a cosine theta, y of theta is equal to b sine theta. This is specifically for an ellipse centered at 0, 0. This doesn't work for any other ellipse. You can do parametric equations for other ellipses, but that's one. So keep practicing this. There's a term I want to present to you, like now that we're at the end. T and theta are called the parameters. That's where the parametric name comes from. And that's the new independent variable. Okay, I'm going to stop the recording.